Okay, let's go for the next chapter. The next chapter will be chapter 21, electric charges and the electric field for charges at rest. In this case, we're dealing with electrostatics. Electrostatics work with forces, right, and fields, correct, between charges at rest. Great. Now, let's work with the charges. Remember, we locate the charges in the atom. The atom, we have a nucleus, correct? We have positive charges and neutrons in the nucleus, perfect, like this. And around this nucleus, we have the electrons, right? We have electrons, the symbol, we can use the symbol for the electron, correct? The symbol for the electron, perfect. Now this is a neutral atom. Neutral means that net charge is zero. Net charge, zero. Well, it has charges, correct, but the net charge is zero. What happens if we remove one electron from this neutral atom? Well, in that case, the whole atom behaves as a charged particle, right? In this case, it's gonna be positive, and that's why we call this positive ion. If this neutral atom gains an electron, right, an electron, in this case, the third atom behaves as a negative charge. And it has a name also, this is negative ion. Right, now let's find the magnitude for this charge, right? This charge is equals the magnitude about 1.60 times 10 to the negative 19 coulombs. In this case, coulomb is the unit of the charge. The symbol for charge is Q. We can use this as the symbol, this Q, right? Or this Q. That's the symbol for charge. But the unit is gonna be coulomb. 1 coulomb, how we can find 1 coulomb? 1 coulomb is equals to we have solved, right, for 1 coulomb. Right here is gonna be 1 electron divided by 1.6 times 10 to the negative 19. And this is equals to 6.25 times 10 to the 18 electrons. So a coulomb is a big unit. Usually in the lab, in the calculations, we work with microcoulombs because this big number, right? 10 to the 18 electrons. Okay, great. Now, when we're dealing with charges, it has some properties. For example, the charge is conserved, correct? And charge is also quantized. Let's see what happens in these cases. Charge is a property of matter, the same thing as mass. It's a property of the matter, and it's conserved, the same thing as mass. So charge is conserved. Is conserved, right? When we're dealing with isolated system, when the charge is isolated system, right? We have interaction, everything, right? Then the charge is constant. It's conserved. Also, that charge is quantized. Means that the final charge, the total charge, is a multiple of the unit charge. In this case, 1.6 times 10 to 19 coulombs. So charge is quantized. Charge is quantized. Quantized is coming from the word of quantum. Quantum means quantity. Perfect. In this case, the total charge, imagine the total charge Q is equals to a whole number of, or multiple of the elementary unit charge, which is, in this case, the proton or the electron, the magnitude. Correct? Perfect. And we can use it this way, plus minus, right? And in this case, we can say this is, for example, or n, and takes the values of 1, 2, 3, right, and so on. So I mean that in this case we have that the charge is coming in plus minus e, right, or plus minus twice this quantity or plus minus 3 times, right, this quantity and so on. That's the meaning to be quantized. We cannot split it. We don't have half, right? Half of this elementary charge in a space free. We have some fractions inside of some particle, but they are not free yet. Okay, perfect. Then let's go to charging. How we can charge an object? Perfect. Let's do it. We have three ways, mainly three ways how we can charge object. And these are by contact, by friction, and by induction, by charging. So we have charging object, gonna be by contact, right, by friction, and by induction. Correct? By contact, imagine that we have a charged object. One more time, this is a charged object, this is positive charge. We have a conductor, minus a conductor. When we touch this, this conductor with this charged object, what do we have? Well, when now these are in contact, we have that this object is charged by contact, right? It's charged by contact. Perfect. Now, what about by friction? The same idea. If we have an object, right? Imagine this is the object. This is rubber, plastic, right? And you have another material, and you wrap these two, correct? And this becomes charged by friction, right? And they might imagine this is the case. Well, it's charged, and now we can charge all the object by contact. Great. What about by induction? In this case, induction means no contact, right? So to charge object by induction, we have the same idea as before. We have this charged object, and we have a conductor, right? In this case, we have two conductors, correct? That they are in contact. They are isolated, right, from the rest. And of course, remember this is a conductor. A conductor has free electrons, right? When these electrons feel, right, this the presence of this negative charge, right, they're attracted. By the way, remember we have this law of the charges. We say that like charges repel, right? Repel. And unlike charges attract, right? Attract. Okay, we use this law of the charges. Again, like charges repel and like charges attract. In this case, because we have electrons, right? The conductor has free electrons, right? These free electrons are being attracted by this positive charge, correct? And then also we have free electrons right here. This part becomes negative charge, and this side becomes positively charged. This is kind of polarization. Also, we call this polarization. We have two poles. Perfect. Now, what happens if we remove this conductor? When we remove this conductor, now this conductor becomes charged, but without contact. It's not in contact with this original positively charged, right? So it becomes positively charged, right, by induction. Later, if we remove this object, right, this is gonna be negatively charged. And this is again charging by induction. Okay, now let's go to the concept of positive and negative charge, right? As we know, we have two types of charges, positive and negative, right? The elementary one for subatomic particle, right, that give us the unit charge for positive is the proton, and for negative is the electron. Okay, now how we can differentiate them? How we can know that this is charged? Imagine, how do we know this is positively charged or negatively charged? How we can make it? Okay, in this way. We need to use a convention, and this is the convention. The convention is that if we have a cat fur, we can use cat or rabbit, right? Fur, and we have plastic or we have rubber, right? When we wrap these two materials, right, after rubbing, now they becomes charged by friction. After that is found, right, that the charge, or by convention, is defined, right, that this is gonna be positively charged, right? This material and this material gonna be negatively charged, and that's the convention. That's the convention. If we have cat's fur and we have rubber, when we charge these two by friction, right, we get that the charge of cat's fur is gonna be positive, and for the rubber is gonna be negative. We have another convention. In case we don't have these materials, we have a silk, and glass. Correct? And glass. Imagine this is glass right here. The same thing, but now the convention is the opposite. If we charge this by friction, at the end it becomes negatively charged and it becomes positively charged. Right? We have these two conventions to differentiate the charge. You can do this very easily. You are combing your hair right at home, right? Sometimes the comb becomes charged, and the charge gonna be right similar to this rubber, right? A rod, correct? And your hair is gonna become right positively charged. Perfect. That's the convention. Now imagine that we charge this object, right? This is plastic, using this technique, and we know for sure by convention that this is negatively charged. What happens if we have another object that is charged, this one, but we want to know which type of charge is this one, positive or negative? How we can determine, right, if this is positively charged or negatively charged? Well, if we know one element, one object like this one, that we know is coming from this convention, and this is negatively charged. Well, if we approach these two, these are repel, right, means that these two have the same charge. If this is negative, there's gonna be negative charge. If they attract, right, we know that they have opposite charge, right? So if this is negative, it's gonna be positive. And we can define in this way the type of charges for any charged object. Okay, perfect. Now let's go to the case for insulators and conductor. What is the difference? Well, this is the difference. A conductor is a substance or material that conducts, right? Especially we have what? Materials, right? Like metals, or we can have ionic solutions, correct? So we have the conductors. We have mainly what? Metals, right? And ionic, right? Solutions. Okay, perfect. And we have a non-conductor. It's the opposite, right? Non-conductor is the material or substance that doesn't conduct electrons, correct? This conduct, right? Electrons. Non-conductor. Wow, non-conductor. Okay, gonna be doesn't conduct, right? Not conduct. electrons. Okay, perfect. Now let's see if we have this being a conductor, and we charge this by contact, right? So if this is positively charged, right, we have some charges sent to this conductor, and this charge cover the whole surface of the conductor, right? It's being conducted from this position to all the positions, to all the points of the conductor on the surface. What about a non-conductor? If we have a non-conductor, or insulator, sometimes called insulator, right? Non-conductor. Let's say piece of wood, plastic, glass, and so on. Correct? If we touch this with a object that is positively charged, so the charge stays in one spot, right? On that spot. It doesn't cover the surface of this object like the conductor. Correct? So this is the difference. The charges are being conducted, the charges are not conducted. They stay in one spot. Non-conductor, conductor. Right? Perfect. Now let's go to try to find the interaction, right? Interaction are just forces, right, between two charges. And let's see what happens. Okay, let's do it. Let's do it. Imagine that we have two charges. These mainly are point charges. This is positive charge and negative charge. Imagine, correct? So according to the law that we wrote before, like charges attract, and like charges repel, and like charges attract, right? In this case, there are a difference, so they attract, right? And we have a force. The force of attraction. Now let's try to find the magnitude of this force. So what do we have? Well, this force is found that if we call this Q1 and this is Q2, remember that's the symbol for charge is Q. So what do we have? It's found that this force is proportional to Q1. Also it's found that force is proportional to Q2. Also is found by Charles Coulomb, right? If we call this the distance r, it's found that this force, the force between these 2 point charges, is proportional, inversely proportional to this distance squared between the 2 charges. Remember, these are factors, okay? This force depends on this charge, also depends on the charge, depends on the distance. These are the factors that are acting, right, or affecting this force, right? Because these are factors, the factors are multiplied. So force is proportional then to the product of these 2 charges divided by the distance squared between the charges. How do we eliminate this symbol? Well, using a constant. What do we need a constant for? To match the unit. Okay, so what do we have? Force is equal then to a constant K, correct, times charge 1, charge 2 divided by the distance squared. Right? And this is the magnitude, because this is the magnitude we represent, right, this formula in this way, correct? And this is called the Coulomb's law. Coulomb's law. This is for charges at rest. Perfect. Because force is a vector, we need to find the direction. Okay, when we're dealing with electrostatics, right, we have 2 types of forces, right? Electrostatic forces, types of electric forces. We have attractive and repulsive. Attractive and repulsive. Correct? Attractive or repulsive forces. So using this concept, we can determine the direction. For example, in this case, what is the direction toward each other? What happens if we have the same type of charge. So it's gonna be the direction opposite, right? Away from each other, right? This is the way how we can find the direction, correct? And this is the way how we can find the magnitude. So at the end we have the forces of vector, right? Magnitude and direction. Or we can use this concept too, right? Attractive force and repulsive force. Only two types. Perfect. It's very important equation, very important law. This is the Coulomb's law. Perfect. So force is equal to the magnitude K, Q1, Q2, right? R squared. And this is valid only for point charges. Great. Now let's find the magnitude for K. This found in the experiment. And is found to be equals to K. K is about 8.99 times 10 to the 8.99 to 10 to the 9 to the 9. What should be the units? That's gonna be newtons meters squared divided by coulombs squared. Usually for calculations, right, it's about 90 times 10 to the 9 newtons meters squared over c squared. Correct? Look, but when we're dealing with charges, point charges, right? We have a point charge, right? Usually we're dealing with the fields, for example, that covers a surface, right, over the space. Usually we take into account, right, the sphere, imaginary sphere, right, that covers this charge. In this case, in many calculations and formulas that are coming later, it's better to use the surface of the sphere. And the surface is equals to 4 pi r squared, right? That's the formula for the surface of a sphere. Because we are dealing in many cases with surface of the sphere, so it's a good idea to have this quantity present. But look, this is coming from here. We already have r squared. Now what happens if we have, right, force equals to K, right, and we multiply by 4 pi and we divide this by 4 pi, correct, times this charge, actually this is the magnitude, correct, times this quantity divided by r squared. In this case, right, we have 4 pi r squared, which is the surface of the sphere, correct? Now, but what is this? Look, what is this? When we have this quantity, correct? This quantity now give us a new constant. K is a constant, force a constant, pi is a constant, so that gives us another constant. Let's define this product. K, or 4 pi K, equals to 1 over epsilon naught, right? 1 over epsilon naught. Then what do we have in this case? We have that this formula now is presented this way, right? Q1, Q2 over 4 pi epsilon naught, right, r squared. This epsilon naught is called the permittivity of free space. It has also a value, epsilon naught permittivity, right, of free space. Perfect. And the magnitude is equals to 8 point. The magnitude for this quantity is gonna be equal, or is equals to 8.85. Correct. I'm looking for this quantity. Gonna be equals to 8.85 times 10 to the times 10 to the negative 12, right? And the units are the inverse of K, so that'll be what? C squared newtons meters squared, correct? Now we can represent in this case, right, that the force, the magnitude is equals to Q1, Q2 over 4 pi epsilon naught, right, r squared. Again, we use this equation in the case that we involve, right, the surface of the sphere. We have many cases, right, where we work with this formula because we're dealing with surface of the sphere, correct? Or simplifies the equations using this notation. Okay, perfect, great. Now let's see what happens when we are solving problems, right? When we solve problems, we use the concept of superposition. Superposition of forces. Let's do it. Let's do it. Superposition of forces. Superposition, right, of forces. The idea is the same thing as we use in mechanics, right, when we're dealing with the free body diagram. Remember, when we're dealing with free body diagram, we locate or find all the forces acting on an object. Correct? Imagine for free body diagram. Free body, right, diagram. What do we have? Well, we have an object, correct? We have forces acting in this way, right, in this way, in this way. Also, we have the normal force, correct? And we have a weight. Mine is F1, this is F2, F3, right, F4, we have angles, theta 2, right, theta 1, and so on. And then, right, we use the free body diagram, correct? So we have this F1, F2, and we have this is F2, F1, right? What is this, F4, right, F4, correct? The normal and the weight, in that way. The same thing happens when we're dealing with charges. Correct? Imagine, for example, now we have this arrangement. We have this charge right here. This is negative, positive, okay, negative. Let's label this Q1, Q2, Q3, right, and Q4. Imagine that we're looking for the net force acting on this charge. Again, this is similar to free body diagram, right? Let's see all the forces acting on this charge. And we can say, for example, that these two, the force acting on this charge due to this charge is going to be in this direction because these two repel. And we can represent this as force done on 4, right, due to charge, charge 2 in this case, charge 2, correct? What about between these two? Well, they attract, right, so it's going to be in this direction. So it's going to be, let's say, forces, vector force, or what, on 4, charge 4 due to charge 1. What about between these two? Well, they attract, correct? And we'll label this a force on 4 due to charge 3 in this case, charge 3, correct? And then we represent this as a free body diagram, right? Free body diagram, correct? So we have this force. We can label this force 2, you want to, okay? This F3, and this is gonna be F1, for instance. And then let's use the same technique as when we're dealing with forces, with vectors, right? Let's find the net force in the direction, right? And the net force in the y direction, and then we combine them. Well, what should be then the net force, right? The net force, as we know, is equals to the net, right, force in the x direction, I hat, plus right force in the y direction, right, the net component, j hat. For instance, we are dealing in to the x and y. Correct? And that's the way how we solve problems using superposition of forces. Similarly to, again, in mechanics when we're dealing with forces, right? Finding the net force. Newton's second law, using the free body diagram. The same technique. Okay, perfect. Now, let's go to the electric field. The electric field. As a reference, let's use the gravitational field. Remember, in the previous semesters, we cover the gravitational field, and by the ground, right, represent by the gravitational field, the symbol is G, right, as a vector, correct? And it's constant in magnitude and in direction. And represent this, remember, as G, right? The gravitational field is equals to negative G, where G, remember, is the average, and is equals to, in this case, 9.80 meters per second square. Okay, again, how this G is found? Well, imagine that we take the Earth as a planet, right? The Earth as a planet. How we can find, in this case, the gravitational field? Also, we found it before. In this case, we use a test mass, right? Test mass, right? And we place this test mass around the Earth to find the gravitational field. And it's found, right, that mass is attracted, right? So let's move this test mass right here. It's being attracted, right, and so on. Using this technique, we can find or draw, right, the gravitational field produced by the Earth, right? It's gonna be in this direction, right? Toward the center of the Earth. This is G, the gravitational field. And how we can find the formula, the magnitude? Well, remember, this is we found using force, and we found this what's related to weight, right? We know that force is equals to mg by the surface of the Earth, right? That's the weight. Also, we can take the same quantity, the same formula to represent G at any point above the Earth. In this case, G as a vector is a vector, right? Vectors is equals to a force divided by the mass. And this is for the Earth, right? The gravitational field. Let's use the same technique to find the electric field. But when we're dealing with charges, we have two types, correct? We have two types. Now let's try to find then the electric field for the positive charge and the negative charge. Let's do it using this technique. Again, right here, look, right here we have a test mass. Imagine this is for the Earth. This is for the Earth, again, Earth. In this case, we have a positive charge, similar, right, to let's say the Earth. Now we need again to use a reference particle that help us to find the electric field. In this case, we use the mass because we're dealing with masses. In this case, we need to use a charge because we're dealing with charges, correct? But because we have two charges, we have to take one to be the test charge. In this case, is the positive charge, right? So positive charge right here is the test charge. And let's do the same thing as we did for the Earth, right? Let's move this test charge around this original charge. And what happens? Well, they are repelled, right? They repel. This charge, test charge, the symbol for test charge is Q naught, correct? Q naught is the test charge. So it's being repelled, correct? It's being repelled. Okay, let's do the same thing as for the Earth. What should be then the electric field for this positive charge? Well, it's gonna be in this direction, correct? Away from the charge. And this is the electric field. The symbol for the electric field is E. Right? E. So it's the electric field. Also, these are called the electric forces, right? Those are forces. This field is also forces, right? Perfect. Now let's try to create a formula, the same thing as we did for the Earth, right? For the Earth, remember we found that's equals to force divided by the mass. The same thing happens right here, right? The electric field as a vector is equals to the force, right? The force divided by the test charge, correct? And we have usually the same thing as for the forces, right? Because for the forces we have right here the magnitude, correct? So the magnitude. The same thing we do for the well, we can use vectors for the moment, right? Divided by the test charge. Okay, this is the electric field for a positive charge. What about for a negative charge? The same technique, correct? Okay, instead of positive, right here, let's use negative charge. In this case, what happened? Well, we use the same test charge by convention, right? The positive charge. In this case, well, they are attracted, right? They attract to each other, right? Attract to each other, like that. So what should be at the end then the electric field for this negative charge? Well, the electric lines of force, right, go toward this point charge. Right, and this is the electric field for a negative charge. And this is the same formula for both cases. Now what happens if you want to use the Coulomb's law? Well, let's do it. So the electric field, now let's use the magnitude is equals to we can use this one, Q1, Q2, right, divided by 4 pi epsilon naught r squared, but also is divided by Q naught. In this case, we represent this, this is a point between two charges. One more time. Imagine now this is Q, right, Q1, let's say, and this is Q naught. So the force is between these two charges, correct? So in this case, one's gonna be Q1, the other one's gonna be Q naught, right? And then this is divided by Q naught. So this Q naught is cancelled, and what do we have? Well, at the end, we can also represent this, and this was gonna be charge, could be Q1, Q2, Q3, and so on. Just Q in general, divided by what? Divided by 4 pi epsilon naught r squared. Right? And this, of course, is the magnitude of the electric field. We can represent it in this way using Coulomb's law. Correct? Perfect. Now, what happens if we have this notation too? If I look in my note, this notation also we can represent this in this way: 1 over 4 pi epsilon naught, right? It's gonna be the charge, right? Using the unit vector notation. Correct. It's another way to represent. This is the absolute right. This is in the direction as a vector. Perfect. Now, what happened? What happens if we want to find the electric field of some charges in one point? Right, the same thing, right? We use the superposition, right, for the electric field. And we have what the electric field, the total electric field is equals to the electric field produced by charge 1 plus the electric field produced by charge 2, right? And the electric field produced by charge 3, right? And so on. Correct? Perfect. Now we want to find the total electric field. We can use this technique. We can use this technique right here. Is equals to 1 over 4 pi epsilon naught, right, times the sum of Q sub I over R sub I squared, right, in this direction. Okay, this is using superposition, right? Superposition. We can use this way, this formula, or we can use the other one, right? This one. Using components, right? The electric field is equals to the sum, right, of this, the torque component in the X direction, right, plus the torque component in the Y direction. And we combine them. And later, of course, we can find, remember the magnitude. What should be the magnitude? Using this formula, well, the magnitude for the electric field, which is magnitude equals to the square root of the sum, right, in the X direction square plus the sum in the Y direction square, right? This is the magnitude. We know this from vectors, right? Vector analysis. Also, the direction. What should be the direction? The direction is theta, right? This is the inverse tangent, correct, of this component. correct? And this is the direction. Again, we know this from vectors, okay? This is the direction of this field, electric field. Got it? Perfect. Now what happens when we have two charges, right? And we're looking, imagine we're looking for the electric field between these two charges. We know that by convention, the electric field, right, leaves the positive charge and enters the negative charge. Imagine this is the situation right here. So this is gonna be the electric field, right? The electric field between these two charges, correct? It goes from positive to negative. Imagine that we're looking for the electric field at this point. How we can find it? Well, look, at this point, we know that the electric lines, right, goes in this direction, right, and for the other charge, right, it goes in this direction, correct? This is the electric field produced by positive charge, and this is gonna be the electric field produced by negative charge, correct? When we look for the net or the resultant, right, for these two vectors, well, we know that it's gonna be then the electric field. So the electric field is gonna be the sum of the electric field produced by positive charge and the electric field produced by negative charge at that point. Correct? Imagine we have another point right here, What should be the electric field? Well, in this case, it's being attracted, right? Or goes toward the negative charge, right? And in this case, goes away from the negative charge, correct? So what should be then the net electric field? Was gonna be, correct, using the parallelogram technique. Remember, this is, one more time, electric field produced by positive charge. This is the electric field produced by negative charge. And this is the total, right, electric field. It's tangent. You can see the electric field is tangent to this curve. It's tangent. It's tangent. That's the electric field. Got it? Perfect. What about if these two charges are the same type? Mine is positive and negative, and positive, right? So in this case, they repel, right? Then what do we have? Well, it's coming, it's being repelled. It's coming, repel, right? It's repel in this way, right? They repel. Correct? In that way. So this is again the electric field. Let's say in between these two charges. Correct? Perfect. See, we have then the electric field, right, and the electric charges. Also, we found some formulas that help us to solve problems in electrostatics. Perfect. Now let's start right here. For this chapter, it's gonna be half of the chapter, and see you in part 2 for chapter 21. Okay, see you later. Bye.